Hi everyone. I'm very happy to present you the project that I worked on for the whole summer today. It's about the use of tungsten and some of its alloys with regards to nuclear fusion reactor. So basically my project was a general exploration of the subject and also an introduction to the CalFab method to optimize a binary system. First of all, let me introduce myself. My name is Vincent Rioux-Frenette. I am a second-year student in chemical engineering at Polytechnique Montréal. I'm passionate in the science fundamental aspects behind the processes, so that's why I was so enthusiastic when I got the opportunity to do an internship at CRCT with Professor Hervé. Now, before talking about the project, let's learn a little bit more about the reaction of nuclear fusion. This is exactly the same reaction that happens in the sun to create its energy. So two small elements, deuterium and tritium, react together to form an heavier element, helium. This reaction releases a lot of energy and is very interesting because this is clean energy with zero carbon emission. But a large flux of neutron is also released. So it's going to be a challenge to find material that would be able to face this irradiation, but also to face the extreme operation conditions of temperature and pressure. The reaction happens in the magnetic room in the reactor. The room is limited with the diverter and the first wall. The materials to build these parts need very specific properties, such as high heat resistance, high irradiation resistance, but also a low hydrogen retention, and we will see why a little bit later. Here comes tungsten. Tungsten is a very interesting option because it has the highest melting point of all elements, so very interesting to work at high temperature, also a low erosion rate and a low hydrogen retention. But sadly, like all of us, tungsten is not perfect. The armor material for the reactor first wall will face plasma, and with its high atomic number, tungsten has bad interaction with it. Also, its brittleness could be an issue, so it's very important to reduce the ductile brittle transition temperature to increase the ductility of the material. And the best way to solve this problem will go through the study of the tungsten alloys. In our project, we have a list of elements of which we have to assess the solubility in tungsten BCC. The first step is to verify if the system is already or not in any FACSH database. Then we have to identify the saturated phase. Real challenge comes when we don't have the system in our database already. We will have to calculate it, and to do that, we will use the CalFAT approach. CalFAT stands for calculation of phase diagram. The first thing to do when we want to do a CalFAT assessment is the literature review of the system. So we collect as much information on every phase and as much thermodynamic data as possible. With these data, we can build a database, and eventually we will be able to optimize and to calculate the system. More with regards to our project now, that was very important to determine the solubility of hydrogen in tungsten. The lack of data made it very difficult, but we still found out some useful information. As I mentioned before, it's important to get material with the lowest hydrogen retention as possible, because eventually, the accumulation of hydrogens in tungsten causes stress and structural damages. That happens because hydrogen atoms are trapped in defects in the tungsten structure. This information is very important because one of the first things that we try to do when we do a CalFAT assessment is to know on which lattice we will put each element. Here, we know that hydrogen atoms are on interstitial sites, so that implies that we will have to put tungsten and hydrogens on two different sublattices. For the beryllium tungsten system, which is not in any FACSH database also, the first iteration of the literature would suppose that they would be on the same sublattice because of the relatively small difference between their two atomic radius. But in a paper from the Royal Society of Chemistry, we know that beryllium atoms occupy interstitial sites into the tungsten BCC lattice. This information leads us to conclude that beryllium atoms will be on another sublattice. That shows how it's important to iterate the literature review and to don't neglect it, because we want to make sure that we start our assessment on good basis. Information that we are looking for when we do this kind of assessment are thermodynamic data. In our case, we care about two major categories, the solutions and the compound. For the solutions, we need the enthalpy of mixing and the activity. If we are not able to get them from the literature, it's possible to get them from theoretic calculation or numeric simulation. For the compounds, we need the enthalpy of formation, the entropy, and the Cp. fortunately, this time, FactSage can estimate their value in the compound module. So we build a compound with the mixer tool, and we will estimate their value from the cup numerator. Sometime when we want to optimize a system, we might need to adjust some values. So here, the first example is for the stoichiometric compound Be12W to get it stable at a defined temperature. So here we got the initial enthalpy of formation, temperature at which we want to stabilize our compound, and the activity of the compound at this temperature. If we put these values in the following equation in red, we obtain a new enthalpy of formation. And if we add this value to the initial one, we will get the corrected value. And by putting the corrected value in the compound module, we will be able to stabilize our compound at the right temperature. The second example is for a solution, the liquid phase in the solution model. We put an interaction between tungsten and beryllium. To do that, we use a Gibbs polynomial as an XX parameter. The first term is the enthalpic term. To define it, we use the enthalpy of mixing. We didn't have any experimental data, so we used the energy of formation of the Be2W from the Material Project website, and we just convert it in the right unit, and with some calculation, it's able to estimate the enthalpy of mixing. The second term is the entropic term, and we usually use it to adjust the solubility of the solution at a higher temperature. As I just mentioned, lack of experimental data has been a real issue in this assessment. It can be explained by various factors, like the large melting point difference between tungsten and beryllium, by the high beryllium volatility at the temperature of equilibrium with tungsten, but also beryllium is pretty toxic, so any experimentations with it implies a lot of L-Tesor. Finally, there is my phase diagram assessment. Still a work in progress. Mine is represented with the continuous line. The black points have been extracted from the phase diagram from the literature. We can see the assessment is not perfect. In fact, even in the one from the literature, they mention a critical lack of experimental data. So in the both cases, it's more of an experimental, it's more of an estimation, sorry. I didn't have time to explore further in that way in my internship, but it's possible to palliate the lack of experimental data with numeric simulation that they are actually able to do in CRCT. So for the stoichiometric compound here, for example, it's possible to predict the enthalpy of formation with DFT calculation, but also the heat capacity with quasi-harmonic approximation. For a non-stoichiometric phase, Be2W, it's possible to predict the enthalpy of mixing with DFT. Same thing for a BCC phase. For the liquid phase, that's a little bit different, but it's still possible to predict some data with ab initio molecular dynamics system. So here, this is just to show you that the lack of experimental data and their unavailability in the literature can be palliated with numeric simulations. Despite these challenges and the sometimes long reading, I love my internship experience. It allowed me to develop my patience, my humility with regards to all these unknown subjects. This humility led me to ask for help when I was struggling, which was harder to do for me before. Now I have a better acknowledgement of what is a research work, and this experience really confirmed that I want to go further in that way. I'm also pleased with the opportunity that I got to learn from this amazing group, where everyone help each other. So hopefully I can come back to work at CRCT again, because it just made me want to learn more. Thank you.
Thank you so much, Vincent. I think it was a really nice presentation. And again, maybe we don't have time for live question, but we'll have some time during the lunch to answer questions. And if anyone wants to specifically ask question to Vincent, please do in the chat. So we'll move forward to another bachelor level student. I think it's important to mention it. Up to now, these are internship, and I'm pretty impressed by